3. We're talking about the controller. Last video we talked about the microcontroller unit, the MCU, and the minimum requirements of getting it up and running and then programming some code into it. So now we're going to explore the supporting chips around the MCU. Look at MainBrain as a whole, or a controller as a whole. And but first, there's one thing I wanted to clear up. On the last video, when we did our code here on the Trisby Bits for RB7, it's not really RB7 for the Tris register. It should say Trisby 7, I believe, and that would be equal to 0. All right. So now, let's take a look at the controller on the component level. Alright, so as you know, my example is my controller called MainBrain. So, let's see. So we got MainBrain. Alright. So, we had our MCU, we looked at that last time, and the MCU is a PIC32MX series by Microchip. So we know from the last video that MainBrain's microcontroller runs on 3.3 volts. So we know if it's a PIC32MX and it runs on 3.3 volts. It actually will go 3.3 to 3.6, but most regulators are 3.3, most power supplies are 3.3. So the idea is you might not always have a 3.3 volt power supply sitting around or available for it to plug in. So we want to give a little bit of range for MainBrain to plug into different things. So MainBrain can run on between 5 to 12 volt DC. That gives a pretty good range. Actually, the regulator can go up to like 32 volts or something, but you'd have to have a humongous heat sink for the voltage regulator to drop that much power, that much voltage. It causes a lot of heat, and that's not very efficient. So 5 is optimum, but you can go up to 12 with a small heat sink. All right. So it's got MainBrain by itself with the big display and the brightness turned up all the way and doing hard work, processor continually running, runs at about 300 milliamps. So I designed the regulator in MainBrain to go up to 1.5, and it's possible it would current limit at 1.2 amps. So the power supply should be able to deliver like 1.5 amps. You could get away with lower. 1 amp would probably work fine, even 500 milliamps, but you're pushing it. 1 amp, 1.5, that's pretty good. I'd say 1 amp minimum to 1.5. So let's go 1 to 1.5 amps. That's the requirement for this power supply. Okay? So when I designed MainBrain, I thought it would be a good idea to be able to know how much current if MainBrain is pulling off the power supply, and any board interface underneath MainBrain that uses MainBrain's power, or even from this power supply, because MainBrain passes through the 5 volts or the input voltage to the other end of the board where the interface connector. But we'll get to that. But I wanted to know how much current was going through it at any time, and then you can make your program decisions or whatever. There's a lot of applications that you could do with that. So I think that's a pretty important accessory to have, an option, a very important option to have on MainBrain because MainBrain is basically a universal controller that's being used in this example to control a robot, but it can do other things, many other things. So I try to make it as universal as possible. So to monitor the current, we come in and we have, oh, that's a shitty resistor. I just do better like drawing them like this. There's my resistor. Okay, so we have a resistor that drops some voltage across there. Then we can calculate the current from Ohm's law based on that voltage drop. Okay, so on MainBrain we have a 50 milliohm resistor. Alright, and then down here we have a low power, everything's low power nowadays, low power, high side current monitor. Alright, so high side means that it's on the input of the power supply. Well, on the positive input. A low side would be if you had a power supply here and it goes to the load. Here's your load. And then you have a ground here. And then it monitors on the ground end of it instead of on the load end. So your current sense would be here. That's the low side. So we're doing the high side, which is on the positive input of the power supply. Okay? So this is the current monitor. They call this S plus. This is the plus side. That's the minus side. And then you can set the gain of how it monitors this voltage right here. You can multiply it depending on what you got to match it to the input of what you're measuring it with. In this case, we're using MainBrain's 10-bit analog to digital converter. We'll get to that later too. Alright, so then you have a resistor here that goes to ground, and that's called R gain. So that's the gain. This sets the voltage divider right here. So your output comes from here, and this is your voltage drop across here. All right. So this chip right here is made by Diodes Incorporated. I'm sure you guys have heard of those guys. And it's a ZXCT 1110. Diode. Alright. You want this, since MainBrain runs on 3.3 volts, then the D to A converter is from 0 to 3.3 volts. So you want your maximum range. So with zero current, you'll get zero voltage drop. And with maximum current, 1.5 amp, you'll want to get like 3.2 or some volts close to rail. You don't want to rail it up all the way. You want a little tiny bit of headroom. So that is the first step going in. So we have we have 5 to 12 volts right here coming in. So then the next step is for the voltage regulator to regulate the input voltage down to the 3.3 volts that we need. So we have ourselves a regulator here. Let's get rid of that arrow. And the regulator puts the output of 3.3 volts at up to 1.2 amps. All right. Regulator symbol has a ground. It's a fixed output regulator. It always puts out 3.3 volts. All right. And it is an LD 1086 regulator. It runs on from minus 40 degrees C to plus 125 degrees C. So once the regulator is thermally protected, so once it hits 125 C, it shuts down and it'll pulse the output, but it just pulses until the fault ends. Once it cools below 125, it'll start back up and continuous regulated 3.3 volts. Okay? It's also overcurrent protected, so that's why I put 1.2 amps here. They call it a 1.5 amp, but the data sheet says it's 1.2 amps. So it'll shut down at 1.2 to 1.5 amps. It'll start shutting down. All right. So then, to give a little bit of bulk, use it as a bulk cap, and also for ripple and dropout, you put a cap here, 10 microfarad, and it's a tantalum or electrolytic. I use tantalum, and then that'll help with any dropouts. If the power supply takes a dip, this should take care of it within this reason. Then on the output, have another 10 microfarad tantalum, and that's the same thing in basically as this. So where this is, the power supply might take a dip, and this will supply a little bit of extra current for it. So if the load pulls down for a short amount of time, does a little dip, actually it would be up. If the current spiked like that, this would supply a little bit of current to supply for this, like a battery, kind of like a cat. All right, so this 3.3 volt goes into the MCU. Alright, so this one here also goes into the MCU. It's one of the analog inputs to the 10-bit analog to digital converter. Alright, so we're not done yet. I also wanted to know how hot this regulator was getting. I wanted to be able to monitor the temperature of this thing so that I could like predict when it was going to shut down. Because you don't want to be going along running your robot and it's doing something really precise, and then all of a sudden the regulator gets too hot, shuts down, and your robot stops in the middle. That would not be good. Because MainBrain is basically going to supply the commands to the robot. So if the commands stop going to the robot's going to do something you might not like. So I wanted to know what the temperature of this thing was all the time, or at least be able to know. So I took and put a temperature sensor on the back of the board underneath the regulator. So if this is the board, the regulator sits on top. It's a surface mount. It's the legs. And it has a tab on the back. Alright, so this is the regulator. I put underneath the regulator is a copper pad, and it gets soldered to it. And then I ran vias through the board, plated through holes to another pad right here. So on the back, on the bottom of the board is the temperature monitor. Okay? Okay, so the device is a DS18B20. Alright? And it is called a programmable resolution one-wire digital thermometer. Alright? So it comes in a TO92 3-pin through-hole part, but as I showed on that's the regulator up here and the device down here, it is a SO package. An SO8. So it has 4 pins on each side, but soldered to this pad here. We got these vias. The vias transfer the heat from the regulator into the pad that the temperature sensor sets on. So there's only 3 connections to the device. So we have 4. So we have 8 pins total. And so I'm going to get my glasses on. So these pins were no connects. This one's VDD. This is, they call it DQ. That's the data. And then we have ground right here. and these are no connects. So that's what I did. The pad, you have the pad that it sits on right here, and I just solder all these on here. The no connects are soldered to this pad, and this pad is actually the plus 3.3 volts. And so the tab is too. I always wondered why they did that. But they do. That's the way it is. So all you have to do is connect VDD, ground, and then your data comes out and it goes into your microprocessor. Now it's a single wire, a one wire digital thermometer. So all the commands are done over that single wire, and it's all serial. So we'll get into that too. All right. So that's basically the power supply. We have a 5 to 12 volt power supply. It goes into an iSense and a current monitor. It goes into 3.3 volt regulator. The regulator is monitored by a thermometer, and that data is sent out to the MCU. This is sent out the power to the MCU, and here we have the MCU, and it's grounded, and everything here is grounded, and that's grounded, however. All right. Oh, and then we have the value of the current goes up into the MCU. So a seemingly simple thing, just to supply power, turns into a little bit of more thought, but what you gain from this is a lot of optional leg room that you have for writing code and applications. Okay, so that's it for the microcontroller power supply. The next video is the oscillator.